This is the 13th episode in a series about designing and building a clock for my relay computer. Last time I made a start on the clock schematic and got to the point where I've got the backplane connectors, relay-based clock and basic card UI. In this episode I'll finish off the schematic by adding the crystal oscillator circuit and hooking everything together. So as before, I've taken the liberty of pasting in a screenshot of the crystal clock design just to keep track of things, and let's kick off by going component hunting again. Firstly, I'm after resistors, and typing that as a search phrase gives quite a lot of results. Alternatively, I can pop onto LCSC and track down the exact part. So it's through-hole resistors, and then I'll filter down a bit. Let's go for 1 megaohm. A quarter of a watt carbon resistor. There we go, one match. I can now copy the part code over and get the match in Easy EDA. Now actually that's a bit of overkill for a resistor, but it does give me a decent PCB footprint, so let's stick with it. I'll rename that to R1, which is more typical for resistors, and set the value to 2.2 kiloohms. Duplicating that out, I can lay down the 1 megaohm resistor, and let's wire those together and we can hunt for the next part, which is the crystal. 32.768 kilohertz, cylindrical crystal. Actually still quite a few matches, but let's see what we got. Now the first one's surface mount, so not what I'm after, but this one will do and should have a decent enough footprint. Yeah, here we go. And I can pop that down and wire it out to the resistors. Next up I need some ceramic disc capacitors. 33 picofarads, or picofarads, depending on how you like it. 50 volts, actually yeah, that should do it. And I get 4 matches. And I'll go for this one. Oh actually, that's not found. Let's try the next one. Yeah, that's better. Yeah, that'll do. 2 of those then side by side and rename to C1 and C2 and wire out to the crystal. Just need to finally pop 2 grounds on, and that's the first part of the circuit. Next, let's get the 4060, and here I can search directly for 4060BE, which is the dual inline package version, and there we go, 3 matches. I'll go for this one, and then connect up pin 16 to power, and note this time it's CCV for the crystal clock power, and then I can add ground to pin 8. Next I'll ground out pin 12 to hold the reset line low. Pin 10 hooks up between the 2 resistors, and pin 11 between the biasing resistor and the crystal. Cool. Right, let's get the 4024 in. And wire up power to pin 14 and ground to pin 7. I need to ground off pin 2 to hold reset low, and actually that's it. So just need to bring pin 15 of the 4060 over to the input pin 1 of the 4024. Looking good. Next is the 4512, which I'll pop over here. Pin 8 to ground, and power to pin 16, and then grounds on pin 10 and pin 15. And that'll keep the 4512 enabled and output operating. I now need to lay out the selector switches, and I'll do this with 3 net ports for now, representing bits 0, 1 and 2 of the input. They connect to pin 13, 12 and 11, and I also need to pull these down with resistors, so let's get 3 of them in on the action at 1 kilo ohms apiece. Connecting up to the selector lines and grounded off on the other side. Right, now just need to wire each of the outputs from the 4024 to the corresponding inputs on the 4512. Again, best to just get the wires connected roughly first, and then I can always come back and have a tidy later. Finally then, I need a resistor which will connect to the output pin 14, and I then need a transistor. I'll back off to LCSC again, and I'll search for a BC548, and yep, that one will do. Yeah, that's the one. And actually I can probably just search for that directly. Yeah, there we go, one of those please. Ground out at the emitter, and we're ready for the relay. Oh, actually, I've missed one of the inputs on the 4512. I need to bring over the output from the 4060. There we go. So, back to the relay. Let's pinch one from here and pop it down here. Wiring out the diode and ground, and then actually in this case I want to ground the relay through the collector of the transistor and then hook up the other side of the relay to power. Yep, there we go. Finally, the clock signal comes off the relay contacts like so, and that's the crystal clock. Now fast forward, and I've had a bit of a tidy. Just moving things around a bit and adding some labels. Again, beauty in the eye of the beholder and all that. Anyhow, I now need to hook up the crystal clock to its neighbouring circuits. So let's set power up first, and that'll come in from the second switch, allowing the user to select either the relay clock or the crystal clock, but obviously not both at the same time. Next, I'll hook in the crystal clock output, here driving the 2 LEDs. Cool. I now need to do something with these frequency selection lines. Let's bring those through to the UI sheet. Right, the switch I've chosen is one of these A6RVs, which is a side-mounted binary coded decimal switch. This will operate the selection lines in binary order as you turn the switch, although in this case the 8 and 9 positions will duplicate the 0 and 1 positions because I'll ignore the 4th bit of the switch. The model I'm using is the 102 RS variant, and unfortunately there's no matches for this as LCSC don't stock it. As an alternative, I found a match on Ultra Librarian, although it's not offered in a format directly compatible with EasyEDA, but I can import it from other formats. And after some "here's one I prepared earlier" type magic, I can place this schematic. Unfortunately, I wasn't as successful as importing the footprint, but I can cheat a little here by digging up the footprint for an IDC header. Just need the 6 pins on a 0.1 inch pitch, and then I can map the pins on the schematic over to the pins on the footprint. A bit of a hack admittedly, but it'll work for what I need. You can make custom footprints from scratch, but I can't be bothered to be honest. Right, there we go, that'll do. I can now wire that out. My crystal clock power comes in on the middle pin, and I might as well duplicate that on the other side as it's internally connected in the switch anyway. Then bit 0 goes to pin 1, bit 1 to pin 2, actually no, bit 1 to pin 6, and finally bit 2 to pin 5. Wow, that schematic is confusingly labelled. Anyhow, that'll do the trick. Let's move it and label it up accordingly. Nice. Now I need some way of freezing this crystal clock when the halt latch comes on. Let's add a new net port on the freeze line, and I'll name it CCF. And then bring that over to the crystal clock schematic, and actually I need another relay. Here we go. Wire out the relay coil, and then take the normally closed contact from here over to the new relay coil. This will ensure that the halt line only makes it through when the clock line is low. Effectively that means that it will wait until the clock line high state is complete before accepting the freeze line, as it were. I can then take the crystal clock power in here and intercept the power to the ICs like this. And then off to the 4060 on the left, and the same to the 4512 on the right. This will then effectively cut power to the crystal clock when the freeze line is operated, but only once the current clock high pulse has finished. Right, we're pretty much done, I think. Just one more job. I just need to add the decoupling capacitors I mentioned in my last video. These need to be placed physically close to the ICs that they're covering, and they help keep high frequency noise at bay. These will be some 0.1 microfarad caps, and I'll place them like this on the schematic. They're all grounded out on the other side like so. And add a label. And that's it. All done. A job for me off camera now is to give this schematic a good eyeballing and check everything over and compare it to the prototypes I've built, because next time I'll be designing the PCB off the back of all of this. Phew, quite a lot covered this time, so thanks for watching again if you've made it this far, and I'll see you all next time.